last times, the last of last times. How you solve this kind of matrix? You don't need to solve it. You'll do it by Laplace expansion, right? Laplace expansion. But you don't need to do Laplace expansion. And why don't you need to do Laplace expansion? Well, here's the thing. You see, these are terms over here. There is a 2 common in here. So what you can take is a 2 common factor. You can take out and write this equal to 2 times you have determinant of 1, 0, 1, 3, 0, 1, minus 1, 1. Here you have 3, minus 3, 2, minus 2. And here you have minus 2, 1, minus 1, minus 1. I took 2 as a common factor out of this particular, you see, what do you even call it, column. I'm remaining with this, you see, determinant right here. Now in this determinant, I have to basically make it such, maybe by adding whatever terms or by subtracting whatever terms, that if I can make any two of them as equal, so it just comes out as good. If any two rows and any two columns are just same, and that is what the question is about, then this eventual matrix is basically this matrix itself, its determinant will come out to be 0. So here's what you can do. You have to basically add them in maybe such a manner. You have to add two rows or you have to add two columns, such that what in the end you'll be getting is two columns or two rows that have the same elements, right? So now you basically have to think, if you add this in this, what you'll be getting something like 1104. Now you're getting 1104. If you're getting 1104, so let's just write it here. Here you have this term. Now 1, shall we write it here 1104 and here we shall write 01 minus 11, or shall we write here 1013 and here 1104? Now that's a question. So let's just write here 1013 1104. Then you write 3 minus 3 2 minus 2. Here you write minus 2 1 minus 1 minus 1, right? Now here again you see the elements still are not the same. So what in this case you can finally do is, if you add this one to this one, maybe you might be getting 4 minus 3. Well, that won't be beneficial, so let's add these two. You're getting 4 minus 2, 2 and 2. So that's one thing that we finally got. Nice. There's 2 over here, don't forget. 2 determinant of 1013 1104. Now here you have 4, adding them minus 2, 2 minus 2 minus 2, 1 minus 1 minus 1. See, 2. Take 2 as a common factor out of this. You have 4 determinant of 1013 1104, 2. Now here instead of 2, I can as well take minus 2 as a common factor, because when I take minus 2 as a common factor and this becomes, so this will come negative, this will basically come positive, this will come again, since this was positive, this will come negative, this will come negative. So in this case I got minus 2 1 minus 1 minus 1, and see, two rows are same. Any two rows are same or any two columns are same, that means you have a 0 in the determinant, the value of the determinant. So without using Laplace expansion, you used the properties of determinants. What properties are there? If you can take any common factor out of any row or any column, take that out and multiply it by the determinant that you are left with by taking out the common factor. Another most important property is that you can add any two rows or any two columns, and one of the column or row can remain the same, the other will be replaced by the sum, and you get to decide which row or column you replace and which one you are having it to remain the same. You can go by these two rules. Whenever two rows or two columns come out to be having the same elements, then you have the determinant equal to 0. This is the last time I explained this to you. I'll not explain this again. This is how you dealt with the determinant of a 4 by 4 matrix without having to evaluate it using Laplace expansion. Or otherwise, Laplace expansion would lead you to nothing but basically, you see, having a weighted sum of 4 3 by 3 matrices, the determinants of 4 by 3 4 3 by 3 matrices. Then to solve these 3 by 3 matrices, you would have the weighted sum of each. For each of them, you would have the weighted sum of 3 2 by 2 matrices. For the 2 by 2 matrices, you would have two weighted sums of, you see, two matrices, the determinants of them that are 1 by 1. So 1 by 1 is the element itself. See, 2 by 2, you can evaluate it very easily. Cross multiplication, subtraction. 3 by 3 also, you quite remember the formulas. But 4 by 4, how do you deal with it? Laplace expansion has to be used, but here you equate it to 0. So reduce it to the simplest form possible. Because even if the elements were not same, even if it were not 0, the matrix has become so simple, the determinant has become so simple that now if you evaluate the Laplace expansion in this, it's a lot easier comparatively. So better simplify it first, then solve. Because maybe while simplification you get a 0, you don't get a 0, you get some other really nice number instead of having to evaluate this. This is the last time I explained you. Now you can go to